Alright, well we might as well go ahead and get started. This is another pretty full lecture, so I put the slides up online already just in case you want to keep up with them or whatever. There's a few slides that I excluded from the lecture itself because I thought, these aren't really necessary, but hopefully they made it into the PDF and you can look at them on your own later. So remember that at the very end, this was sort of the last thing that we talked about, and unfortunately, I hate covering really important things right at the end of a lecture, but we started to talk about the calling convention that is used by all Unix variants on 64-bit x86 processors. Okay? Now keep in mind that this is going to be different for different ISAs, so this convention is for, like I said, Unix-based or Unix-like operating systems running on 64-bit x86 processors. Okay, so we're going to start looking today at the question of how do we implement some of the other C abstractions in x86 64. We did start talking about subroutines, including how to pass integer and pointer arguments, those kinds of things, local and global variables. And so this was the calling convention that we were talking about. Now the caller and the callee both have to be involved because we have two shared resources. We have the stack and we have the register file. Okay? And so remember that we had some registers that if the caller wanted to preserve their value, then the caller was responsible for saving them. And there were other registers that if the callee wanted to change it, then the callee was responsible for saving and restoring the old value. Okay? So we had things like that. These were the general details of the calling convention. Who sets up which parts of the call? Remember, caller sets up arguments, because how could the callee? Caller also cleans up arguments, because, again, it knows better than the callee what it did to set up arguments. We have caller versus callee save registers. We always return, remember, we're only talking about integer things, because that keeps life simple. That's basically what we'll do in all of CS24 when we talk about assembly code, because the x86 floating point support is complicated, and who wants to talk about complicated things? This is hard enough. So return values are in RAX or EAX if it's an int. Okay, so we have these details. Here is the program we're going to look at today, just as an example of how something like this might be implemented in x86 assembly code running on a 64-bit processor. Okay, so a simple accumulator. Hopefully all of you have enough experience with C to understand basically what's going on. We have int value, that is a global variable. In general, we really dislike global variables, but we're going to have quite a few of them. In systems programming, you frequently do have one or two, right? So, but this is just for the sake of example. That's where we are going to accumulate things into, and obviously we can look at the value to see what the current value is as well. Okay, so we have a global variable, functions to update or reset the accumulator, and then a main function. What's the main function doing? Well, we're just going to add in 10 values. Each value is generated by rand, which is a function that just generates random integers. And we do rand modulo 1000, which means that the values are going to be 0 to 999. Okay, so that's all we do. We're going to accumulate 10 of those, and then we're done. Okay, so we have global variables, function arguments, and local variables. Three different kinds of values that our program has to manage. Now, fortunately, we already know how to do all of these. That's why it's great to be looking at this example now. We know how to do all of these in our instruction set architecture. So global variables, well, we'll just pick a memory address for it to live at. Okay, remember, it'll have a certain size as well, dictated by its type. So ints are 4 bytes on x86 64. And so we'll just reference it via absolute address. Now, that's actually not entirely correct. We'll see why momentarily. Okay. Then we have function arguments. So right now we only have one function argument because our program is super simple, but we have accum takes one int argument. And remember that on the calling convention, the first 6 arguments are always passed in registers. So if I remember correctly, it's what, like RDI? Was that the first argument? Somebody who knows. I should have it memorized by now, but I don't. I'm sorry. But anyway, I believe it's RDI. And that's where accum will get its argument, so that's cool. And then we have local variables. Now, if we didn't have enough space, we would store these on the stack. But we have this luxurious 16 general purpose registers to choose from. And so we can just see if there's an available register, which there will be, and then we can use that register. And of course, we have to be careful. If it's a callee save register, then we need to save the value and restore the value after we're done using it. But there's so many caller save registers, why not just use one of them? Okay, I think there's only 6 callee save registers, so it's pretty easy to pick one that's not callee save. Okay, so that's basically what we're going to do. Okay. So how is this implemented in x86-64? Well, it turns out that you can also ask the compiler to tell you how it would implement the function. And this is a really useful thing when you're learning how assembly code works. And so you can see that we pass a couple of arguments to the compiler to ask it politely to generate some code for us to look at. So $S says generate some assembly code and save it so that I can look at it. You'll see that the result goes into a .s file. .s is the typical extension for the x86 assembly code. And then we have a whole bunch of other arguments, basically all centered around the issue of making sure the compiler generates code that isn't stupid. Okay? I don't know how many of you have done the generating of the example.c code that I think is included in homework 2, but you may have noticed, if you looked carefully at it, that it's kind of dumb. Kind of like really dumb. Like maybe 4 times as long as the code actually has to be. The TAs and I were going over the solution set on Friday in the TA meeting, and I include in the solution set both the unoptimized version and the optimized version, and I kind of forgot how dumb the unoptimized version really is. So you notice that sometimes. So we have -01 to say, hey, apply some optimizations, please, so it doesn't look hideous. No inline means that we won't inline functions like printf, which gets really weird. And also a cum and reset can easily be inlined. And then we have fortify source, which we turn off because printf is a great example of a function that can easily be compromised if it's used incorrectly. So we turn off some of the security checks as well. Okay, so we're actually making it pretty simplistic. And what I will tell you is that the results that we're going to look at are generated on a system like the CS24 virtual machine. So a Linux computer, 64-bit, using this particular set of arguments. Okay? It really can vary a lot based on what compiler you use and what platform you're compiling for. OS X is a notable example because it is wildly different from what you see on Linux. Okay? And it still produces the exact same results, it's just the OS has different characteristics in how it's implemented. Okay? So here's some of the output, and we'll just use this to start getting used to what it is the compiler spits out. Okay? A lot of this you could probably figure out all by yourself. Anything starting with a dot is a directive for the assembler, telling the assembler something other than an instruction. Okay, so we can have instructions, but then we need to tell the assembler a lot of other things. A really great example is .text. This is probably the most important segment of our program, the instructions that we have. So the reason why it's called text is a historical quality because it was called the program text back in the day. So that is what .text means, and you'll even see .text appear in binary files. Like there will be a section of your ELF file that's labeled .text, and that's where the program code is. Okay? Now, anything with a colon is a label. So a cum, remember, that was the name of one of our functions. Reset is the name of another one of our functions. And you'll also notice that these things have a .global for them, saying, hey, this is a symbol that somebody may want to use from outside this file. And this is one of the things that sometimes people run into on assignments 2 through 4, is that they write some assembly code and they forget the .global directive to say this symbol should be made visible from outside of this assembly file. Because you can imagine easily you have 2 assembly files with the same label names. Could happen. So the way that we avoid name clashes is just say some of them are global, and then otherwise if you don't say anything, they're private. Now, we also have a .size directive, which generally we don't care about. The compiler will generate this kind of stuff just to make sure the assembler has all the details it possibly needs. But in this case, you can see that we're saying what the size of the function is. Like how many bytes does accum occupy? How many bytes does reset occupy? Okay, and so this is something that the compiler makes the assembler generate. So it says .size, accum. Remember that accum is a label, but it's also the name of a function. So that's what you see when you see the .type accum at function. And so .size is basically saying dot minus accum. So dot is the current address, and accum is the starting address. Obviously, the current address minus the starting address will tell you the size in bytes. Okay, so that's just another example of some of the details here. Any other questions? All right, so there's some directive details for you. Do you really need to use all these directives? Thankfully not. Basically what you'll have in your assembly code is a label that is the function to call. You'll have .global label name so that you can call it from outside the function. And that'll be it. That's really all you kind of need in your assembly files. You may need .text. I can't remember if you need .text or not. But I think it may just assume that as well. Okay. At the end of our output, if you were to run this again through the GCC compiler on Linux, and you would see at the bottom you would have something called .com value 44. And what this is basically saying is there's a global variable named value. And guess what? It doesn't have an initial value assigned to it. It's just, I have this memory location, I'm calling it value, and it's 4 bytes, and I'd like it to be aligned on a 4-byte boundary. Yeah, that's what the 4, 4 means, right? So basically, you can see here that the input to the assembler says, here's a variable, but I don't know where it's going to live yet. And so everywhere inside of our assembly code, we refer to it by its name, just like we had in our little contrived virtual machine from earlier. Okay, so the assembler will assemble, the linker will link, and we'll end up having an actual address for value, and then we can go fix up the machine code with the actual address of value. Okay, does that make sense? So again, this is one of the things, we're just looking at how the compiler does this. Don't worry, you never have to actually create a global variable in your assembly code. Like what we'll expect you to do is just write functions that have local variables and arguments. Thankfully, that's all you have to do. Okay. Let's see, accumulator code. So here is int accum. How much simpler could it get? In fact, we just returned the new value to make it more interesting. So this would translate into this assembly code. It looks like I was correct. RDI is the first argument. So notice we pull EDI into EAX. Now why do we do that? Well, keep in mind that this may be more complicated code than we absolutely have to implement. And I haven't sat down and figured out if you could do this in 2 instructions instead of 3. But you might be able to. Okay. We do need to initialize EAX because we don't know what's in it before, right? It could be anything. Whatever the caller was doing with it, we really don't know. So that's why we move EDI into EAX, and then we add the current state of value into it. Now that's also where our return value will be, so we're already done with EAX, and then we just need to store that back into value to make sure it's safe. So yeah, I guess this is a pretty nice, clean way of implementing it. Okay, any questions? Again, pretty straightforward. Do we have a frame pointer? Do we even access the stack? No, not really, right? We do, in fact, access the stack with ret, but we don't store any variables or arguments on the stack, so we don't need a frame pointer. Why set one up if you don't need it? And you'll probably notice that a lot in your assembly code is that you just don't need frame pointers, so why set up a frame? Okay, let's see. Yeah, the values are all type int. So that is another important detail that's good to point out here. Remember that we're saying that these are R registers, but then the E registers are the low 32 bits. Well, our function takes an int. That's only 4 bytes. It's not 8 bytes. We return an int. So that's 4 bytes. It's not 8 bytes. So that's why you see all of these things working with the E registers, not the R registers. Okay? Except for RIP, which is always only 64 bits, because that's just the size of the instruction pointer on x86 64. Okay, let's see. Yeah, so we don't need a frame pointer. Talked about that. The other thing that's interesting to look at here is you'll notice that we say value and then in parentheses RIP, which you may remember is very similar to the indirect addressing that we talked about. Was it last lecture? It's amazing how time flies, right? So RIP is a register, and then we're saying do something with RIP and value. Okay? But this is a special kind of addressing mode, and this is also partly why we don't make you do global variables, because this is called RIP relative addressing. Okay? What the assembler will do is say, okay, they want to access this value that's in memory somewhere, but they want to do it relative to the current value of RIP, or the current instruction pointer. Okay? Which means that somehow it's got to figure out the relative distance between the current instruction and the thing being accessed. And then that distance will be stored in the machine code, and then the processor can just use that to look things up. Now, why would it do this? Seems a little bit like complicated of a way to access a value. Okay? Well, there's two things that we really like about this. One is that distance between the value and the current instruction is going to be independent of where the code is actually loaded by the operating system. And so it could load it at one address, and it would still be able to access value no problem. It could be loaded at another address, and it can access value with no problem. Okay? Why do we care about that? Well, it turns out, do you have a comment on that?
So ASLR works.
ASLR. So that's, can you tell everyone what ASLR means?
Address space layout randomization. So it's hard to make like memory tasks.
Yeah, that's exactly right. So if we can randomize the layout of our programs in memory, then that means that important global variables that we could use for making the code do something we don't like, we don't know their addresses easily. And so it's a little bit more difficult to compromise a program. So that's one thing. Like, it really improves security to be able to generate application code and operating system code that's position independent. Okay? The other point is also on the slide is that, well, that offset is probably going to be tiny. Maybe it's going to be less than 64K. And so I can encode my distance as 2 bytes instead of requiring 6 bytes or something like that. Okay, so those are some benefits. Yes?
So value isn't being used as an immediate value here. Is this basically like when you define a common symbol, then it just calculates the offset?
Yeah, so that's a really hard question to answer because in a sense, I'm trying to make sure I understand your question correctly. Because I would say that it is being used as an immediate value. It's just not, you're not using the absolute address of value. The assembler will, and the process is complicated as well, because what the assembler will do is generate some relative distance between where value will probably live and where this instruction will live. But then it's not until link time that all that stuff gets fixed up, and the actual value. So there is still a register and an immediate value combined together into an indirect address.
That's just when you define a symbol with copy.
Mm-hmm.
It does this type of
Yeah. So I think that this is the easiest kind. I don't remember if I tried. I may have tried long ago to create a 64-bit, a value that's accessed through just a straight 64-bit address. I don't remember if there's even other ways of addressing besides RIP relative anymore. So I don't know everything about this architecture yet. I've only been teaching it for 1 and change years. So you may find that there's other clever things you can do with it for sure. Okay? Any other questions? Alrighty. So fun stuff. Here's the reset code. Notice we pull out the old thing. You can probably already guess where that would go, right? Well, it'll go into RAX, or let's just say EAX. That seems more reasonable, so we'll do that. And then we just need to move 0 back into value, and we're done. Right? So reset is super simple. Now, again, recall that value is 4 bytes, so that's why we have move L's all over here. And remember also what happens when we do our first move instruction. We're moving value RIP into EAX, but x86 64 has this unusual characteristic that when you write to the low 32 bits, it will zero out the high 32 bits. So that has the implicit quality of also setting RAX to be the same value. So that makes it really simple. Okay, here's the main function. This is where it's going to get a little squirrely. Okay, let me see if I go back here real quick, and let's just look at what functions are invoked. Okay, we have reset, we have rand, which is a C standard API call, we have printf, which is also a C standard API call, and a cum. So those are the 4 functions that we're calling here. Okay. Also, keep in mind what we're doing here. We have I and we have n. We use I to loop 10 times, and then we use n as a temporary placeholder for figuring out what value to add into our accumulator. Okay, so those are our variables. Now let's look at what the compiler actually does. Okay, first part is, just as one would hope, okay, so the compiler decided to use R12. That happens to be a callee save register, so it behaves properly even with main, because it turns out that there's a function that calls main. Something has to call main so that the program can start. So we save our 12, we save our BP and our RBX. So we use both of those in our main implementation as well. Then we call reset. Reset returns a value in EAX, but we don't care. We don't use it. We just say reset, so it calls reset and then doesn't bother to do anything with EAX. This is the remainder of the code. And you might ask yourself, how did Donnie figure out stuff like this? And it's kind of like, you know, Sherlock Holmes or something like that. You just try to figure out the parts that you think mean something, or you figure out things, what they mean, and then that gives you a clue about what the rest of it could be. Okay? So we're going to cover this at a pretty high level because I kind of don't care about the really gory details here. But I'll give you references if you're interested in learning more about them. Okay? But we have, you can see the highlighted code here. Move 10 into EBP, and then at the bottom we subtract 1 from EBP, and then we jump if not equal, or jump if not 0, back to the start. Okay? So EBP is our loop variable. Okay? L4 is the address of the start of our loop. Okay? So this is kind of an interesting thing that we do here. Even though our C code is written to do I from 0 to 10, well, let me ask you this. Is there any part of our loop body that actually references I? No, right? So really, the compiler's free to iterate over that loop in whatever order it wants, using whatever mechanism it wants. Could even create a variable with 10 bits set to 1 and just shift it right each time, and when it hits 0, it could stop, right? That'd be crazy, but one could do that. Okay. So the loop body doesn't refer to I, so the compiler decides I'm going to simplify my code a bit by counting down, because then I won't have to compare it to a number. If I start with that number and just decrement it each time, then I can just jump as long as things aren't 0 yet. Okay? So that's what goes on here. Sub L updates the flags register because arithmetic operations do. Okay? And so then the very next operation is, hey, let's just look at the 0 flag, and if the 0 flag is not set, go back to the top of the loop again, because I have more things to do. Okay, so that becomes pretty straightforward. Any questions? Yes, question?
Yeah, so if you have something where it's actually shifted like I equals 1 to less than 11, will the compiler shift it down by 1 so that way it can just stop at 0?
That is a really good question, and I don't know the answer to that. My gut is that the compiler would figure that out and apply the optimization. The reason why I say that is because you can give the compiler a recursive function with the recursion in tail position in the function, and it will turn it into an iterative function. I mean, the compiler is crazy smart. Okay? And so for it to do something like recognize that I actually have a shifted range that's not referenced inside the loop body and unshift it and reverse it is totally... It's like, okay, that seems pretty easy compared to some of the other things that it does. Okay? So, but that's just a guess. You would have to verify what it actually does. And the other funny thing is that may be the answer today, or I should say the answer today may be no, it doesn't, and tomorrow's answer is yes, it does, because compilers get smarter and smarter. Okay? I know that when I was an undergrad, compilers were not making tail call optimizations on recursive functions. And when I discovered that they started doing that, I was like, wow, this is pretty dang amazing. Because nobody expects that for C++ or C, right? They expect it for functional programming languages. Okay, any other questions about this? Alrighty. So here's the next giant chunk of assembly code we're going to try to figure out. This is rand modulo 1000. Okay, you can see right at the beginning it calls rand. Where does rand's result end up? Well, it ends up in RAX, and I would say probably it ends up in EAX specifically because I believe rand is defined to return an int, and so it starts doing crazy things. We actually have 2 imols in there. Now, this is what's weird. If you were writing this, what would you do? If I were writing this, what would I do? Well, we know there's a div instruction, right? We just, there was like 83 instructions Donnie talked about last lecture, and one of them was a div, and we know it produces a remainder, so why not just throw a div at it and shrink that giant chunk of nastiness down to like 2 operations? Well, this is the thing that's kind of wild. Division is a really slow operation. And so if you can figure out a faster way of doing division, then maybe that'll actually be the faster thing to do. And that's actually what the compiler is figuring out as it does the code gen. Okay? So like I said, integer division modulus with a constant can be implemented as multiplication. If I'm dividing something by 1,000, I can also multiply it by 1 over 1,000. Okay, that's cool, but the problem is that 1 over 1,000 is definitely not an integer. But the thing is you can take that value and scale it up until you have an integer value, and then do that for multiplication, and you know that the result modulo 2 to the w will be in the right range. Right? So this is the crazy thing that compilers do. And there's a whole book that talks about these kinds of crazy tricks. And to me, it's wild that you have something that's like 8 or 9 instructions, including 2 multiplies, that the compiler is still pretty sure is going to be faster than a divide. Okay? That's how slow division is. That's why we don't like doing it on assembly code if we can possibly avoid it. Okay? Any questions about that? Okay, we will never speak of this again. Thank you for not asking questions. So, the last part of this is simply figuring out accum and then invoking printf with the result. And so the call to accum is pretty easy. Okay, remember that I said that ECX is where the n modulo 1,000 appeared. I'm sorry, n is rand modulo 1,000. So n is between 0 and 999. So that ended up in ECX. We have to drop that into EDI. Because remember, EDI is supposed to be holding the first argument, or RDI if you will, but that'll just be RDI as well. And so we invoke it. Accum returns a value. Accum's value is in RAX or EAX if you want to be pedantic. Okay. So now we set up for the printf call. Okay. So EDI is the first argument to printf. Remember, EDI, ESI, EDX, ECX, blah, 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 blah. I don't remember the rest. So EDI is going to be set to our string constant because printf takes that format string as the first argument. And then ESI is the second argument, that is n. So where was n stored? That was in ECX, so it got moved through EBX into ESI. And then we have EDX. We have to say EDX, that's the result of accum. And accum put its result in EAX, so we just move EAX into EDX. So that's the first move in the green section. Now we're all ready to call printf, right? Everybody with me? Okay, now there's a little weirdness going on because you notice that n was calculated and then we moved n into EBX. Why did the compiler do that? EBX happens to be one of the registers that the callee is responsible for saving. So the compiler is like, you know what, I need this value later, so why don't I just stuff it in EBX, and then when I call my functions, they have to save it if they touch EBX, but I know that the value will remain unchanged, because it's presuming everybody follows the same convention, right? So stuffs it into EBX, pulls it out of EBX, and puts it into ESI. So this is like saving a register's value without having to involve the stack. Okay. You know, this is a lovely thing about compilers. They teach you a lot about how to write clever code. Okay? Any other questions about this? We have not gotten to the printf call yet. You can see that's a few lines later. You see that we have this weird thing where we set EAX to 0. And the reason why we do that is, again, a Baroque detail that you're not required to know. But printf is a variadic function. It takes a variable number of arguments. And because it takes a variable number of arguments, we also need to tell the system how many of those arguments are floating point. And so that's why we do the move 0 into EAX. Okay, the compiler does this for us. Okay. Thankfully, we have no floating point arguments, so it's just set to 0. Okay, and then we call printf. All right, any questions about how this main function does its thing? Like I said, it can be pretty fun to try to figure out how these things work. Yes, question?
Is there a calling convention for variable arguments that can't reduce the number of arguments that pass?
Is there a calling convention for variadic functions where you can't deduce the number of arguments?
Like printf can figure out the number of arguments from the format string.
Yeah, printf can figure out the number of arguments from the format string, but the thing is that I think you're always stuck with the function has to be specifically designed to be able to figure out how many arguments it's passed. So, for example, if you didn't have a format string and you just started off with, how many ever arguments you want, you could have something magical where you say once you hit a specific value, then you stop. Because you can set up. This is way beyond the scope of what we talk about in CS. I should show you sometime because it's actually kind of neat. But yeah, you have to, in some way, with these functions, be able to infer from the arguments how many arguments there should be. Because what happens if you can't? It just keeps trying, and then probably accesses memory it shouldn't, and then it probably crashes, and then you're probably sad. Okay, so that generally is what happens there. Yes?
I have a question. What is the $.lc0?
$.lc0, that is an excellent question. LC0 is the string constant, and that's actually the next thing to talk about. There is another section. So we've already had two sections, right? We have .text and .data. Now we have a third section called .ro data, and that is for initialized constants. That's where our string constant lives. Do you remember how when we had our little contrived processor and we needed to store 1 and 0 and our bit masks and things like that because we were simplistic? Well, we still have to do the same thing on this big, awesome processor. Okay, so .string is blah, and the assembler will copy out those bytes into the generated object file. Okay. But then it has to have a label so that we can refer to it. Because we don't have a label assigned to it, it's a string literal. So .lc0 is generated, and then that's used in the assembly code. Now here's something that's fun and wild. What sizes are pointers on a 64-bit processor? I will accept either 48 bits or 64 bits as the answer. Both are correct, as long as you understand the difference. But how big is EDI? Definitely not 48 bits or 64 bits, right? Well, here's the fun thing. On Linux, when you have string constants, the way that the Linux memory layout is, the pointer size will always be 32 bits. Like, it'll always be below 4 billion. So the compiler is clever, and it says, well, I only need 4 bytes of pointer for this because I know the upper 4 bytes are always going to be 0. And so that's why it's able to do that. Plus, it takes advantage of the fact that the processor, when you write to EDI, is going to set the top 4 bytes of EDI, or RDI, to 0. Everybody got that? So again, even with our stupid string constant, we have some crazy subtleties going on where the compiler is being clever to generate smaller and faster code for us. Okay? Pretty cool. Okay, so if there's no more questions about this, I'm going to go ahead and go on. If you have other questions, I suppose you can ask me later. I think we pretty much beat it to death, though, which is good. Some of this will make more sense also after you do the arithmetic problems in assignment 2, which are kind of fun. But I think we've basically covered this completely. So what we're going to do next is look at how we do flow control in C. I should say, how we do C flow control in x86 assembly code. Okay, we have if statements, We all love, I love if statements. While loops, for loops, and do loops. Okay? So we know how to use these in your C code, or whatever code you're writing, Java, or Python, or SQL, or whatever. I mean, most of these languages have some kind of conditional operations and looping constructs. So how would we translate something like a C flow control construct into x86 assembly code? Okay? This will help us understand what the compiler generates. And of course, you will be called upon at least a couple times in this class to write your own flow control and assembly code. So it'll be helpful to see how this is done. Okay. Now, the way that this is done, remember, we can do calculations, we can do comparisons, like with comp or with test, and then we can do conditional and unconditional jumps. So somehow we have to take an expression in C and translate it into those kinds of lower level, more primitive operations. Okay? So this might be the way that we translate an if statement. Okay? This is not the only way. If you have an if all by itself with no else ifs or elses, then it's really straightforward. Because remember, you just invert the condition, test, and jump over the body if the condition that you wanted to be true is not true. Okay? But now that we have an else, it's a little bit more complicated. So here we say T is test expression. If T, go to the to branch. So you can see that the else body comes first. When we finish the else body, we jump over the if body. And then the true branch, we just have the code for the then statement, and then we fall through to the end. That's one way we could do this. There are other ways we could do this, depending on what might be the optimal flow. Okay? Any questions? The version of the code here, you could actually implement this in C, what I have there on the slide. The book happens to call it go-to style C code. And hopefully all of you realize when you are looking at this that you should not write C code this way, but it happens to be a nice intermediate step if you're taking C code and translating it into x86 assembly code. You don't want to go straight to it unless you've been coding in assembly for years and years. So probably most of you will not want to do that. Okay? And you shouldn't try, just because of ego or anything, because it's just going to make your life hard. So anyway, go-to code is a great intermediate step for understanding how these things are translated. Because that's really easy to translate into assembly. Okay, so yes, and like I was saying, this can be rearranged in all manner of different ways, depending on the need. Okay, do loops. I always like asking people, when was the last time you wrote a do loop? But I'm going to refrain. I write like 1 to 2 do loops a year, and I write a lot of code. Okay? Do loops are very uncommonly used in programming. They tend to be used less frequently just because they run through the loop body at least once. But the reason why we like to talk about them first is because they're really easy to do in assembly code. Okay? You just drop down a label at the top of your do loop. You have the body. And then you generate an if statement that says, well, if the condition still holds, then jump back to the top of the loop. So you fall through the bottom of the loop if the condition is false. How easy is that, right? Do loops are my favorite when it comes to translating into assembly code. Right? Okay. While loops, much more common, but they're a little bit more tedious to translate into assembly code. One thing we could do is say, all right, I'm going to follow the same sort of translation process and say, T is my test expression. If it's false, then I'm going to jump out of the loop, do my loop body, and then at the end, I'll jump back to the top. Okay? That's certainly something that one could do, but the issue with this is that it's slower than it has to be because we have a couple of branching operations in here. Processors don't like branching instructions. They make things slow. And there's a lot of effort. There's a lot of transistors on your silicon that go toward making these kinds of things faster because they can really complicate life. Okay? So we're not going to talk about all the details. I know that there's some information in the textbook about it, or you can talk to me about it afterward. But just look up pipelining, instruction pipelining, because it turns out that an instruction can be in many different phases of evaluation on the processor. And if I am fetching one instruction, then I could be decoding the next instruction, and then I could be evaluating the next instruction, and I can actually have multiple things going at once. branching interferes with all of those things. So we like to avoid branching if possible. So what would be a better way of doing this? Well, what if we took this while loop and peeled off the first iteration and then turned the rest of the loop into a do while? So now we have an if statement to check if we do the first thing, and then we have a do while instead. Okay? Something like this. So if the test expression is false, jump over the whole dang thing. Okay? And then we have a do while. Right? So if you went ahead and translated this, you would find that your main loop body would just have the one conditional operation at the end. We don't have any other conditional operations in the middle that would complicate things. Okay? And continuing this translation, you would end up with something like this. So again, this is the kind of thing you can do. You can pretend you're a compiler. You'll have to do this a few times. And take C code or pseudocode, whatever you start with, translate it into go-to style code. And then you can take the go-to style code and translate it into assembly code very, very straightforwardly. Okay? And then the great thing is that your pseudocode and your go-to style code become your comments. And so you've commented your program and implemented it at the same time. It's a really nice approach. Okay, any questions? All right, let's see. What do we do next? For loops. These are sophisticated while loops. They have all kinds of stuff that they can do for you. You have initialization. Remember, the initialization happens before the body of the for loop. So then you have your test expressions, which is like a while loop, right? And then you have your update expressions, which occur after the body statement and before the next iteration of the loop. So you end up with a translation like this. And there's no reason why a real compiler wouldn't take a for loop and just turn it into that equivalent expression and then reuse its while loop compiling facility, which will then take it, turn it into a do while, and so forth. You can see the compilers basically are just, a series of simple transformations, taking the code that you wrote and turning it into the machine code that the computer can understand. Right? So, and then we know how to do all of these statements. So abstraction, and Donnie doesn't want to talk about it. Right? So you can take this and turn it into the appropriate go-to style code and then do the implementation. Okay, questions? Alrighty, so now we know how to do flow control. It's like achievement unlocked. I can now take C flow control and turn it into assembly code. So we can do some pretty sophisticated things now. We can do functions. We can do global variables, or at least we'll pretend we can do them because we don't like them. So we can do local variables on the stack. We're really cool. And now we can do loops and for loops and flow control. And hey, recursion too. Here's a new problem. I have a function that I'd like to write. I don't know why one would write this in assembly code, but let's say we have find primes. We give it n, and it's supposed to give us back a collection in some representation or another of all the prime numbers up to n. Okay? Can we build this? I assert that we can't. The reason why is because we basically have two ways of storing values right now. We have the register file and we have the stack. That's all we've got, right? So if n is 100 or n is 1,000, the size of the answer is going to be different. We don't have a way of doing this yet. Okay? Also, when we put stuff on the stack and then we return, all that stuff on the stack is supposed to come off of the stack, because we're supposed to leave the stack in the same state as when we invoke the function. Okay? So the lifetime of the memory that holds the answer has to be different than the memory that we usually use on the stack. Okay? So you can see that we have a couple of problems already that we've run into here. So this is where let's invent a new memory facility called the heap. Who's heard of the heap? Who's used the heap? Who loves the heap? I love the heap. Okay, so this is a very large pool of memory from which we can make allocation requests, get a chunk of memory, use it however we want, hopefully correctly, and then return it back to the pool so that it can be used again in the future. Okay? So this is a really powerful mechanism. No longer is the chunk of memory that we're using, no longer is its life cycle tied to the stack. Okay? Now it can be based on what the program wants to do. It can last as long as the program wants. Okay? So this is a runtime facility. Okay, so if you ever thought, well, Java has a giant runtime, Python has a giant runtime, C has no runtime. Well, C has a tiny runtime because it has to be able to do things like this. Okay? So there are a few functions that we use for this. malloc, again, everybody's favorite. You give it a number of bytes that you would like to allocate, and it gives you back a void star, which will either be a pointer to a memory region of at least that size, or it will give back null to indicate that the allocation request could not be satisfied. Okay? We have not really required you to verify that the response is success. Okay? So that's something that we'll be talking about more in the future. But right now we're assuming our programs always have enough memory. Okay? If we want to release a block back to the pool, then we pass the pointer to the start of that block back through free. Okay? And so then the memory heap will be updated to record that that chunk of memory is, again, available for use. Okay? Everybody got that? There's a few other ones as well. There's calloc. There's realloc. You may or may not. Who's used realloc before? Okay, a few of you. You know that you can do all of like the allocate, free, and reallocate all through realloc. Realloc is way too powerful. It should be simpler, but it's not. So realloc is a really useful and frightening beast. So there's a number of other functions besides the ones we have here. Okay, so here's the details. I want to spell this out because, again, CS24 is about the basic building blocks and how they work and why we have them. And so I want you to understand what the differences are between the stack and the heap. So when you have the stack, the space has to be automatically reclaimed when the function returns. And so you can imagine the compiler generates code to make sure that this happens. But the consequence is that we have to lose all our values at the end of the function invocation. They won't last beyond the function invocation. Procedures are specifically encoded by the process. Not the processor. That's ridiculous. They're specifically encoded by the compiler or the human being to use the stack. Okay. And we also expect that from invocation to invocation of function's stack size, the size of its frame is not going to vary by much. Okay. Now there are ways, and they're scary and they're probably bad ideas, but in general we expect that the stack space used by a function invocation is not going to vary by a lot during its execution. Okay? So that's the stack. Programs in heap. Well, the heap is a much more powerful tool. So a lot of times we allocate memory on the heap directly in proportion to some argument. So n, I need to find out how many primes there are up to n. Well, I can allocate a chunk of memory proportional to n. That's no problem there. Also, programs have to explicitly allocate and release blocks of memory on the heap. Okay? At least at our current level of sophistication. We'll get even more sophisticated next week, which is pretty dang exciting. But for now, programs will have to explicitly allocate and explicitly release blocks of memory on the heap. Okay, does that make sense? So this is the distinction between the stack and the heap. Okay. So here is a simple example that we will actually implement in assembly code shortly. But this is a variation of what we had before. So instead of somebody passing in the result vector, where we should store the answer, we're going to malloc it. Okay, so we say result is malloc length times the size of the int. Okay. And then we go ahead and do our calculation into result and then return result. Okay. So this is kind of a neat thing. So we will explore how to implement this, but I want to talk about one important thing before we talk about how to implement this. And that is, what is an array in C? And it turns out to be the same thing in C++. And why do we start indexing at 0? Okay. You can see here that pointers and arrays are very closely related because we have A and B, which we declare to be arrays. We don't give a size. Not that C does much with the size. And then we have result, which is an int star. So what's the relationship between pointers and arrays in C? Okay. So the way that C defines arrays is that you have a contiguous sequence of values that are all the same type. If they're all the same type, then that means they all have the same memory layout and they all have the same size. Okay? So they're contiguous in memory and they can be accessed by indexing. Okay? So we have an array declaration. Variable's name is A. We have n elements and T is the type. So what C does is it allocates a contiguous region of memory that is the size on the slide. So we take size of T, which is a compile time value. So the compiler always knows how to calculate size of. I mean, it should. It's the compiler, right? It needs to know how big types are so it can lay things out in memory. So size of T is a constant generated at compile time, and then it just multiplies that by n, and that's how many bytes the array requires. Okay? So A gets a pointer to the start of that contiguous region of memory. All right? Everybody with me so far? All right, so that's the memory for the array. Now, A holds a pointer. So what address does array element I live at? This is the question. So you can see if I is 0, it should be the first element. A0 should live at A, right? A1 should live at, well, whatever A's value is, plus 1 times size of T, and so forth. Okay? So we can use the index to calculate how far to go into the array. Okay, so each element is size of T, so element I will reside at A plus size of T times I. All right? So, that's exactly what the array indexing operator does for us. Yay, array indexing op. This happens to be possibly my favorite operator of all time. Okay, I don't know why, it just is. Okay, so A sub I is going to take the starting address A, take I, multiply it by size of n, and then add those two together. Now you have the address of the element that you want to access. Okay, so C supports, I should ask first, before we talk about that very last detail, any questions? We good? All right, so this is where your scaled indexed addressing modes are super useful. Reg B can be A, reg I can be I, and then scale, if you have elements that are 1, 2, 4, or 8 bytes in size, you just set the scale in the instruction, and you're done, right? The processor does array indexing for you. Yes?
You have to do a separate multiply if your size of isn't 1, 2, 4, 8.
Yeah, so if you have sizes that are not 1, 2, 4, or 8, you're sad. And so that's where the LEA instruction becomes really useful. Or if you're a little bit more lucky, yeah, usually there's some combination of powers of 2 that is your element size, and so you can do some fun math to get the actual index calculated. And a lot of times LEA is used for that. So for example, if you had a 40-byte struct and you had an array of those, well then you need to take the index and multiply it by 40 somehow. Okay, you're all clever people. I bet you could figure it out. Okay, some fun things to do there. All right, so that's one of the fun things that compilers figure out for us. Okay, last thing to talk about is pointer arithmetic, which is the same as array indexing. So if I have a pointer variable, T star P, C is defined so that if I add 1 to that pointer, it does not move forward 1 byte, because that would make no sense. Instead, the type of the pointer is used to advance 1 element, not 1 byte. Now, it turns out you can also subtract from P, which is a little scary, but you can do that as well. So int star P, if you do P plus 1, that's going to move forward 1 int, or 4 bytes, not just 1 byte. Okay? So you can add or subtract and offset n. And so you can see the implications of this. A sub I is identical to saying A plus I and then dereferencing it. Okay. A plus I will move forward I elements in the array. I use this all the time. I probably shouldn't, but I do. I mean, well, when you write drivers and stuff, you kind of end up doing this kind of thing more than you'd like. Okay? Any questions? Does this make sense? Okay, so just to set up, next time we will look at how to implement this function in x86 64 from scratch. So that'll be next lecture. We'll start that fun task.